you very much to the Center for Theoretical Physics at the Polish Academy of Science for inviting me over to Warsaw and for giving me the opportunity to give this seminar. So it's a great pleasure to be in Warsaw. Poland has a great history in general relativity and in astrophysics and in astronomy. Also, even because of the weather, I lived in Canada for a couple of years and there was a lot of snow and I loved the snow. And I haven't really seen it since, so I'm actually quite happy to see it again. So my name is Marc Casals. So I'm originally from Barcelona. That's where I did my undergraduate degree. But then I moved to Ireland. So I did all my research live in Ireland. That's where I did my master's, my PhD, and some of my postdocs. And about 3 years ago, I'm sharing a position in Dublin with a position in Brazil, in Rio de Janeiro as well. So my research area is mainly in general relativity in the wider sense of the word. But I've been asked to give a talk only about a part of my research. So I'm going to concentrate only on the classical part of general relativity that I work on. I also work on quantum field theory in Kerr spacetime. I'm not going to be talking about that in this talk. So I'm going to concentrate on classical perturbations of black hole spacetimes. And I was told that not everybody here is a general relativist, obviously, so I'm going to try to give an introduction as well to people who are not in general relativity. But feel free to ask questions as I go along. So this is just a brief outline of the talk. I'm going to start describing black holes, what are black holes, and what are perturbations of black holes, and why is it interesting to study them. And then these are the two main the areas of main results that I've got recently. The first one is mainly on black hole stability and the way the wave propagate on black hole background spacetimes. And the second one is related to gravitational waves, and in particular in the extreme mass ratio of black hole inspirals. And I'll finish with some conclusions. Okay, so what are black holes and what are black hole perturbations? So this is some real data, the modeling of some real data by UCLA. These are 13 stars orbiting around some point at the center of our galaxy, the Milky Way. You can see the stars here in purple and a little white cross there. And these are the orbits that the stars are following. So these stars are moving around in some Keplerian-like orbits near some point which is not emitting any radiation. But you can estimate the mass of this object that is there from the orbits of these stars. You can also give an upper bound to the radius of this object, because otherwise the stars would be torn away. And you can estimate that the mass of this compact object at the center is about 4 million times the mass of the Sun, and that the diameter is about the distance from Sun to Mercury. So theoretically, there's no other known object that could sustain such a large mass in such a small radius. So we strongly believe that there's a supermassive black hole at the center of our galaxy.
Does this agree with the radius of the black hole?
That's right, yeah. The Kerr radius. So I'm going to introduce this in a minute, but
it's only an upper bound.
It's an upper bound, yeah. It could be even smaller. That's right. Yeah. So that will depend. I'll talk a little bit about this. That will depend on the angular momentum of the black hole. There are very poor estimates on the angular momentum of this supermassive black hole, but the radius will depend on that angular momentum. So, in fact, it is believed that there isn't just a supermassive black hole at the center of the Milky Way, but that there is a supermassive black hole at the center of every galaxy in the universe. So by supermassive, I mean of the order of 10 to the 5 to 10 to the 9 solar masses. So these are supermassive black holes, about one per galaxy, but there's estimates. People believe that there is thousands or millions of stellar mass black holes in every galaxy. So just a very rough estimate, 0.1% of the stars in our galaxy, in all stars that are formed, are believed to have to be massive enough after a supernova. The remnant is believed to be massive enough to create a black hole. Given the number of stars in our galaxy, that gives us about 10 to the 8 stellar mass black holes scattered around our galaxy, and similar for other galaxies. Okay, so what are black holes? Well, black holes are a prediction of Einstein equations of general relativity. You've probably seen this before, but just a little one slide just reminding you of what this is. So Einstein equations of general relativity are 10 coupled, highly nonlinear partial differential equations. On the left-hand side, you've got quantities that describe the geometry. Essentially, they are second derivatives of the metric, and the metric gives you the distance in space-time. On the right-hand side, you've got the stress-energy tensor of the matter that is creating the curvature of the space-time. One of the important geometrical objects here is the Riemann tensor, which is essentially combinations of second derivatives of the metric, and that gives you the curvature of the space-time. So John Archibald Wheeler gave this sentence, famous sentences: space tells matter how to move, and matter tells space how to curve, because so matter is following the geodesics of the space-time, but also matter tells space how to curve, because matter here is the source of the space-time curvature. Okay, this is general relativity in just one slide. And we want to solve these equations exactly. So quite surprisingly, Einstein derived these equations in 1915. Just a few months later, Schwarzschild found an exact solution in the case of spherical symmetry, so non-rotating black holes, exact solution to these equations. Now, that is an already amazing feat. One of the issues about this, though, is that black holes in astrophysical black holes are believed to be rotating, so they don't have spherical symmetry, but they have axial symmetry. So astrophysical black holes are meant to be one rotating, two electrically neutral, or the electrical charge is very, very, very close to zero. It's negligible. So it took many decades, not until the 60s, that a relativist, in fact it was a mathematical relativist, Roy Kerr, found an exact solution to Einstein equations that describe a black hole which is rotating, so without spherical symmetry, but with axial symmetry. Even more importantly, just a decade later, Carter and Robinson derived some theorems that say that any black hole which is axisymmetric and in vacuum, by which I mean that the matter stress-energy tensor is equal to zero, must be the Kerr metric. So this is a complicated. This is the exact solution of Einstein equations that describe the Kerr metric, which is the unique axisymmetric and vacuum solution of Einstein equations. It doesn't really matter what it looks like. The main features is it depends on two parameters. One, m is the mass, and a is the angular momentum per unit mass of the black hole. The event horizon, which is the boundary of the black hole, is given by this expression here. I'm using units of c, velocity of light equal to 0, and gravitational constant equal to 1, and gravitational constant equal to 1. It would be spectacular if it was equal to 0. So you know that there's a square root of m squared minus a squared, so there is an upper bound to the angular momentum that a black hole can have, which is equal to the mass. I'll be talking about these extremal black holes later on. So extremal black holes are the ones that saturate the upper bound of the angular momentum. Okay, so what does this mean? So this has quite important consequences. This is telling you, well, first of all, Kerr is an axisymmetric solution, so the metric is phi independent. These are spherical or spheroidal-like coordinates, tr, phi, and theta. And it's stationary. It does not depend on time. And what one of the conclusions of what you've said is that any collapse of matter which is massive enough will asymptotically at late times asymptotically tend to the Kerr black hole solution. So all astrophysical black holes in the universe it is strongly believed that they are well described by the Kerr metric. Now, like I said, there's only two parameters in the Kerr metric. There's the mass and the angular momentum. So this is quite a spectacular result. Any other information about the matter fields that collapse to form the Kerr black hole is not at least it's not in the outer region of the space-time. Okay? So all the other information about the star is not out there, it's not outside the black hole, it's not outside the event horizon, all the other information has been radiated away. So it was a big surprise at the time in the 70s, and Price, in fact, for the case of spherical symmetry, found how that happens. So I'm not going to be talking about spherical symmetry, I'm going to talk about axis symmetry and stationarity. I'm going to talk about Kerr, which is what models the astrophysical black holes. Okay, so how is that hair, so to speak? By hair we mean this higher multiple moments of the matter that compose the black holes. How has that been shed away? Well, in order to study that, what you do is you perturb black holes. You take the Kerr metric, for example, and you put some matter fields around it and see how that is scattered away. What happens to those fields? Do they concentrate around the black hole? Do they blow up? Do they run away? Are they scattered away? So this is some image from the Hubble telescope where you can see the accretion disk and some jets in the M87 galaxy, where again in the center there's strongly believed there's a supermassive black hole in the center of it. The Event Horizon Telescope, which is going to provide some interesting data already in April and May, is going to focus on both supermassive black holes, the one at the center of M87 and the one that's at the center of our galaxy. So these field perturbations, and when I say field perturbations, I'm going to be jumping around among different fields. So I'm going to refer to scalar fields, if there is any scalar field other than the any other linear. I'm going to be talking only about linear scalar fields. So we don't know any linear scalar fields yet. It can be fermion fields, and can be the electromagnetic field and gravitational fields. So I'm going to be talking mostly about linear, massless field perturbations of a Kerr black hole.
In which sense massless?
So if you, okay, so yes, so I'm cheating slightly here. So if you could quantize the field, then you could associate a mass to the quantum of that field. That would be a massless field. So the electromagnetic field, the photon is massless, and gravitational, the graviton.
But if I have an accretion disk and that is self-gravitating and it contains a lot of mass, that would count for fermion field?
No. So
Sorry for asking.
no. That's a very good question. So right. So I'm going to be talking about fields perturbing the black hole. So there is some matter creating those fields. So that matter could be an accretion disk, for example, which is obviously massive, but it could create a field, for example, an electromagnetic field. That accretion disk is emitting light, which is an electromagnetic field, it's a massless field in the sense that the photon is a massless quantum. So I'm going to be studying the electromagnetic field created by the accretion disk and how that electromagnetic field is propagating around the Kerr black hole spacetime. So if there were scalar charges that create a scalar field, a massless scalar field, that would be the case as well. That's usually used as a model for other spin fields because it's algebraically easier to deal with. Another one that I'm going to be talking about, especially in the second part of my talk, is going to be the gravitational field. So these are gravitational perturbations of the Kerr background. So I'm going to be talking a little bit more about this. But if you have gravitational perturbations, again, if you could quantize that, and that's not really known how one does this, but if you could quantize that and you associate a graviton to the gravitational field, then that graviton is believed to be massless. And in fact, the latest detection by LIGO, about which I'm going to be talking about later on, has given some upper bound to the mass of the graviton, if it has one. So, sorry, just to finish that. So the source of that gravitational field could be, for example, another massive object. For example, the stars that you see that they showed in the previous movie. So you've got another compact object that's moving around the central black hole. That compact object is obviously massive, but it's creating a gravitational field, which you can treat as a linear gravitational perturbation of the background spacetime created by the supermassive Kerr black hole, and that gravitational field is massless in that sense, that the quantum associated to it is massless. But the source of it obviously is not massless. Similarly, the electromagnetic field is massless in that sense, in the sense the photon is massless, but obviously the source of that is massive. Sorry.
On classical level, it simply means that the dynamics is governed by the Lambert operator of the time.
That's another way to put it, so I'm going to be giving the equation in a second, or another way to say what you just said is it propagates at the speed of light. The wavefront of that field is propagating at the speed of light. Yeah. So I'd like your point, because I'm really going to be talking about classical field perturbations, so that's a nice way to put it. Another way to say it is that the speed of it's propagating at the speed of light. So if we detect those field perturbations, and I'm going to be jumping around between scalar, electromagnetic, and gravitational perturbations quite a bit, if we detect those, that will give you a lot of information about the source of the perturbations, namely the accretion disk or the small compact objects around the Kerr black hole, but also will give you information about the Kerr black hole, or whatever compact object you've got, supermassive compact object you've got there. And it is also important from a theoretical point of view, not just from an astrophysics point of view, but from a theoretical point of view in order to test general relativity. There's alternative theories of gravity, and some people predict, well, that's not a Kerr black hole, that this could be some other objects, compact objects. So if you detect those perturbations, that will help you to test those alternative theories of gravity as well. Okay, so these linear field perturbations, mathematically, how do we deal with this? So like I say, they're going to be linear field perturbations. So by that, what I mean is I'm fixing the background space-time that is of a Kerr black hole. So that is fixed, by which I mean that I'm not letting the matter fields back react onto that black hole space-time. It is so massive and the field is small compared to it that is effectively, the back reaction effects are negligible to that extent. So those fields are propagating on a fixed black hole background with a metric g, and that is of a Kerr space-time. Like the professor just pointed out, these linear field perturbations obey a wave equation. What that means is, this is the case of a scalar field. There are very similar equations for the other spin fields, for the gravitational case and for the electromagnetic case. In the scalar case, in the massless scalar case, this is the D'Alembert, which contains the covariant derivatives of the metric of the background space-time. So here's where the information about the Kerr black hole is coming in the metric, which are the coefficients of the derivatives. And obviously on the source, on the right-hand side, you've got the source of the field, which is could be the accretion disk or the compact object that's creating the gravitational field, or a scalar charge, if there were one, that creates the scalar field. By wave equation, I mean a second-order linear hyperbolic partial differential equation. Now, a very important quantity that I'm going to be calculating and I'm going to give you results for is the green function. So the green function satisfies the same equation as the wave equation. The only difference is that the source now is not the physical source, but it's a four-dimensional delta Dirac distribution. Okay, and it obeys certain causal boundary conditions, so that you can use it to build a physical causal solution. So if you don't like if you don't want to get into the mathematics of it, you can think of the green function as the field created at some point x primed, a very large or infinite in quotes in some well defined way at some point x prime, and the value of that field created at some point x prime, the value of it at the point x. So I'll give you some results for it. Why is the green function important? Well, first of all, you can give some initial data for the field at some given time, and you can evolve that at any times using the green function. So you convolute forward.
Because the problem is perfectly symmetric with respect to the time reversal. So advanced green function is equally important for that purpose.
That's right. But you can get the advanced green function. So the advanced green function advanced green function of x prime is just the retarded green function of x prime x. You just satisfy that symmetry. So you can get the advanced green function just immediately from the retarded green function, and like you say, you can evolve it forward using the retarded green function or backwards in time using the advanced green function. So you can choose whichever way. You can give data at infinity if you wish. That would be a null hypersurface, but at some late times and evolve it backwards, or you can give it at some past times, past in quotes, and evolve it forwards. Yes. So essentially, you have some initial data, and then the green function serves you to evolve the initial data anytime to the future, or to the past, if you wish. It is also important for studying the stability of black holes, so I'm going to give you some results about this. Stability properties of black holes is very important. If black holes are unstable and the timescale of the instability is very short, then, well, that will give you a strong indication that there cannot be black holes out there in the universe. So you really, it's not enough to have a solution of Einstein equations or 2N equations. You want to study the stability properties of your solutions. So I'll talk about this a little bit later in the first part of the results. In the second part of my results, I'll be talking about the cell force. So the cell force gives you a deviation from a geodesic motion of some compact object. Okay, I'll talk about this later. This is important for gravitational wave emission that I'll talk about. And also it's tempting to use it for studying the quantum properties of black holes. I'm not going to talk about this in this.
Deviation of trajectory is due to what?
Yes, so in the first part of the talk I'll talk about this, in the second part I'll talk about this. So let me put, I think it will, I'll have slides and pictures and everything to say this clearly. So let me say, I'm going to talk about this in a minute, I'm going to talk about this in a short while. Okay, so I'll talk about the first part, black hole stability, and how waves propagate in a black hole spacetime. So this is a numerical calculation of the green function together with colleagues of mine. So this is Kerr. This is the equator of Kerr black hole. You can see the Kerr black hole sitting there in the middle very happily. And what we're going to see is a very large impulse being emitted here. So the x and y coordinates are just the equator of Kerr. In the z-axis, you're going to see the magnitude, the amplitude of the scalar field. In here, I'm just going to look at scalar perturbations of Kerr black hole, but a lot of the physical features of it are already kept by the other spin fields. So we're going to send a very large impulse in here, and we're going to let that impulse propagate, okay? Just so you switch on some lantern, switch it off quickly, you switch it on just instantaneously, switch it off quickly, and see how that field propagates on your space-time on the equator of a Kerr black hole. Okay, oops. So I'm going to pause this. There's a lot of information going on here. There's a lot of information. There's a lot of information going on here. So the pulse has been emitted at the center here. Like I said, the z-axis is the magnitude of the field. So you're just looking at the equator. So the pulse is really a two sphere that's propagating spherically. If you were in flat space-time, light is just propagating on a sphere. Here you're just looking at a slice of that, a equatorial slice of that, so you've got a circle extending out to radially, if you wish. So far away from the black hole, nothing too dramatic or interesting is happening. You just got a circle just propagating out. Now you've got a black hole that...
For this pulse, I understand that the value of the field is big, and what about the momentum, time derivative of that?
Right. Yes. So, yeah. Okay. So.
Because the amount of phi is just half of data.
Yes. So, the way we constructed this.
You must give two functions.
Yes. So in order to answer that, let me go back. This might get a little technical, but the way we constructed this, we gave some initial data, which is. The initial data that we gave was 0 for the initial field and a highly peaked Gaussian for the time derivative of the field. The reason why we gave that is because if this is a delta Dirac, because it's simple and because it gives us the retardagram function. Because if I put in a Gaussian, a highly peaked Gaussian in here, that's modeling a delta Dirac distribution, and if I integrate that with the retardagram function, that's going to give, if it's the delta, this is going to give me a delta green function. So this is exactly the way we constructed this.
In any case, you consider half of the data vanish.
Yes,
and,
yes. But the reason, not just because it's simple, but it's because it's giving us the actual retardagram function. But just going back to how exactly we gave the initial data, that's exactly how we gave, yes. 0 for the initial, for the field, and highly peaked Gaussian for the time derivative of that, because that gives us the evolution of the retardagram function.
And this, of course, does not include an observer.
No.
It's not how you would see this perturbation, it is just how it happens. Because then, of course, if you have an observer and then the observer is implied, then you see a
Yes.
picture which is completely different.
Exactly. So, So, for example, in here, so we have this black hole here. Now, maybe you can't see here, but you have a little compact object there that's moving in some orbit. Okay, so that's going to be important for the second part of the talk. I didn't want to talk about this, but in here is the retardagram function. So the value of the field as seen by this compact object. If I calculate this field here, I'm calculating everywhere in the equatorial slice, but if I calculate it here, the value of the field here is given by that. So if you have an observer following this orbit, that's the value of the field that it would see. Now, we are not observers close to a Kerr black hole, we're observers at infinity. Like you say, we're inclined and so on. Things can get messy and complicated, but it is true that for observational reasons, what will matter to us will be the value of the field at radian infinity, and in fact at late times. So I have some analytical study of that. Now, the field here is important for the second part of my talk, which is for the cell force, because if you have a compact object moving around the black hole, you care about the value of the field here, because that's going to modify this trajectory. But I'll talk about this about the second part of the talk. This is why it's important. The field here is also important, but it's more for the second part of the talk. For the first part of the talk, in terms of observations for infinity and for black hole stability, the field mostly is important at radial infinity, late times, inclination, and so on. Okay, so like I was saying, far away from the black hole, the field is just propagating like in flat space-time, nothing too interesting is happening. But as it's getting close to the black hole, the orbit is not radial anymore, the orbit is being curved, so to speak. The geodesics are not radial in this coordinate anymore, but some of the field is going to fall into the black hole, and some of the orbits will deviate. Some of the geodesics of these null geodesics are deviating from radial. Remember, this is a massless field, so the wavefront is propagating along null geodesics, essentially. Not exactly, but the wavefront mainly is propagating along null geodesics. So you're really seeing the null geodesics of this Kerr background spacetime.
Because the strong Huygens principle is not fulfilled.
Exactly. Very good. Exactly. So there's various features going on here. One is the wavefront itself that is essentially propagating at the speed of light, but there is some backscattering. Exactly. There is a tail, there's a Hadamard tail, because the Huygens principle is not satisfied. So that part of the tail is not propagating at the speed of light. So this is, some people find it confusing that light, in fact, doesn't propagate only at the speed of light.
Of course not. That's clearly seen in terms of photons. If you have light which is not a plane wave, then there are photons that have different directions, and when you put them together, the speed is less than c.
No, but not that phenomenon. Because in flat space, in any case, you may
That's right. So in 3+1 dimensional flat space-time, the electromagnetic field is propagating along null geodesics. In not dimensional flat space-time, it's not propagating along null geodesics. And in 3+1 dimensional non-flat space-time, generally it does not only propagate along null geodesics because Huygens principle is not satisfied, the Hadamard tail is not equal to 0, and there's some gravitational backscattering, or whichever way you want to put it. Yes. Okay, so what's happening near the black hole? Okay, so the wave now, some of the part of the wavefront is falling into the black hole, some other part is going to be curved by the space-time. So this part of the wave has gone around the black hole and is going to come back out this way. The part of the wave that came this way is coming like here and is going to come out the other way. And in fact, the two parts of the wavefront have hugged the black hole, and this part of the wavefront has come out this way. This part of the wavefront has come in this way. So in fact here you had the initial wavefront, which is the one up there, that's propagating roughly as if it were flat space-time, but you have another wavefront that has been created here because it's orbiting around the black hole. And in fact this will happen an infinite amount of times. The wavefront keeps orbiting around the black hole an infinite amount of times, just because of the geodesics of the Kerr black hole. Now another thing to notice is the amplitude of the wave is diminishing, and in fact it's diminishing exponentially with time. So this is one of the reasons why you can see, so there's the Einstein light rings, you can see an infinite amount of, in theory you could see an infinite amount of light rings due to the light, the null geodesics curving, orbiting around the black hole an infinite amount of times, but the magnitude of that field is diminishing exponentially, so it's very hard to see any other one other than the first one. Okay, so this, like I said, this is going to happen an infinite amount of times, and seeing how this field is being scattered away and what happens at late times, that's what tells you about the stability properties of the black hole.
Have you imposed any boundary conditions of the...
Oh, no, I can't remember. We just let, I think we just let the
It does not happen at the horizon, it happens more or less at the circular photon orbit. So we are still far from the horizon.
But in principle, there might be some interaction which falls inside.
Yeah, so anything that crosses the horizon would just make it equal to 0, wouldn't let it come back out in any way. Anything that goes away to infinity, so probably our grid was much farther away and the wave is just propagating out, and the boundary conditions there don't have any effect on what's going on here.
So there is some boundary condition.
The boundary conditions would be purely going into the horizon, so we don't let any wave coming back out. Yeah. Okay. So that was a numerical calculation, and we've done some analysis of what's going on. So let's say Kerr spacetime is stationary axis symmetric. So what we do is a Fourier mode decomposition of the retarded green function. We do some harmonic decomposition. We do spherical harmonic decomposition. That's quite innocuous, quite harmless. But the point is we've reduced this to the calculation of a green function of a one-dimensional linear second-order ordinary differential equation. Okay, I'm not even giving you the ODE. That's
but it is no longer just wave equation, one-dimensional wave equation, because there are some extra terms coming.
Yeah, I didn't say wave equation, right? It can't be wave equation because it's one-dimensional, so you don't have any time in it. It just is. It's a two-dimensional linear ordinary differential equation. Ordinary differential equation. Now what we do is, instead of integrating along real frequencies, we're going to deform that contour into the complex frequency plane. Whenever you do that, okay, that's the only technical, that's a bit technical, but it doesn't really matter if you can't follow this bit. You apply the residue theorem of complex analysis in order to account for the singularities of these Fourier modes in the complex frequency plane. This is a plot, this is a depiction of the complex frequency plane in Kerr spacetime. And you look at the singularities of the Fourier modes. So the important thing is you're integrating along the real axis, you close the contour in this way, and you look at the singularities of the green function. Now it has some poles, simple poles here, and these simple poles are the so-called quasi-normal modes. You might have heard this, I'll talk about this in relation to the LIGO detection shortly. So the quasi-normal modes are purely simple, mathematically they're simple poles of the green function modes. You've got some high frequency arc which does not matter, it does not bear any physics, in quotes, and you've got a branch cut down the negative imaginary axis which does bear some physics, and I'll talk about now about the physics coming from the quasi-normal modes and coming from the branch cut. So the point is you can calculate the retarded green function as the contribution from these three terms, the high frequency arc, which does not matter, so I cross it out, from the quasi-normal modes and from the branch cut. So I'll concentrate on the quasi-normal modes and the branch cut. Okay, this is a calculation that I did together with a colleague of mine of the quasi-normal modes in Kerr spacetime. So all these are actual points, they're quasi-normal mode frequencies. In Kerr spacetime for different values of the angular momentum, different values of the multipole L and the azimuthal quantum number M. Remember, the time dependence of the mode is exponential of minus I omega t. What does that mean? Well, if the imaginary part of the frequency is positive, this will blow with time. So this will give you an instability of the black hole. So if you find any of these frequencies have positive imaginary part, your black hole is doomed. Okay, it's going to blow up. It's going to be unstable, and most likely it's not going to exist in the universe. So you don't want any of these quasi-normal modes to have positive imaginary frequency.
How is this related to this original ordinary differential equation for G of R?
Well,
Because at this point, this is a complete solution, right?
yes.
So every property of this solution now is hidden in the solutions of this ordinary differential equation.
Yeah. So you basically,
And omega is a parameter in this differential equation.
that's right.
So now, what are the properties of this ordinary differential equation that reflect on the size of the possible instability?
Okay, good. So, like I say, the Fourier modes are a green function of a one-dimensional linear ODE.
Ordinary differential equation.
Ordinary differential equation. So you won't impose boundary conditions at infinity, radial infinity, and into the horizon. So at infinity you impose that it's a purely outgoing wave, and at the horizon you impose that it's purely ingoing. Now that might seem reasonable, but that's not necessarily always the case. You have a potential here. You have a potential here. So if you had an incoming wave, part of it, so this is Schrödinger-like equation, part of this wave is going through with some transmission coefficient, and part of this wave is reflected. But if you impose, okay, let me divide this by 1 over t. Sorry, this is transmission, this is reflection, so I divide it by the reflection coefficient. If you impose for this to be equal to 0, nothing coming, this purely outgoing wave and a purely incoming wave, you have a quasi-normal mode. So this is how we determine, how we calculate quasi-normal modes. We impose for this to be equal to 0. Physically, that's what will happen. it would be purely going and purely going with nothing else. And well, that's.
What happened with the theta dependent?
But it plays no role in this physics.
The couples?
Well,
The variables are separated.
that's right. Now that was a bit of a mystery at the start, because the stationarity and axis symmetry. What happens is there's a hidden symmetry. Kerr has a hidden symmetry. It's the so-called Killing-Yano tensor. So there's some magical property of Kerr that leads to the separation in r and theta.
So you can understand physics just by looking at the theta equal to pi.
Yes, yes, yes. Some of the physics. You can calculate the quasinormal modes. The theta does not play any part in the quasinormal modes. There's other physics going on.
Change the solution, but
But
so it's
something must be hidden also in these S functions which depend on omega.
Yes.
So if omega is having a certain behavior, as you mentioned here, then that is reflected in the properties of S.
Yes, it will change the theta dependence of the solution, but does not affect the frequencies, the quasinormal mode frequencies.
But I would guess that for some possible omegas, S may blow up, for example, or something.
No, S is always regular. You determine S by imposing regularity. It's like the spherical harmonics. It's a spheroidal, spin-weighted spheroidal harmonics. Okay, I'm struggling with time. I'm struggling with time. So I'm going to run through a little bit. So the point is, we calculate these quasinormal modes. If the imaginary part is positive, there's an instability. If it's negative, the field is decaying exponentially with time. Okay, so Whiting showed that Kerr has no quasinormal modes with positive imaginary frequency. So people say Kerr is mode stable. Okay, let me skip this. What about the branch cut contribution? This is just the quasinormal modes, but there's another contribution to the green function, which is the branch cut. So what is known is that it was known in the 70s for the spherically symmetric case, in the 90s from the Kerr case, is that the branch at late times, the behavior of the retarded green function of the field basically is determined by the branch cut. And instead of being exponentially decaying with time, it decays polynomially with time. Together with collaborators, we found some logarithmic correction to that, which is important for the LIGO detection. I'll mention this later. This is the green function at a fixed point, how the envelope is decaying. There's a log plot, it's decaying exponentially here, and at some stage the red line is the branch cut contribution. The branch cut dominates at very late times, and now it decays as a power law with a logarithmic correction at earlier times. Now, what about extreme Kerr? So in extreme Kerr, remember, it's the maximally rotating black hole. Away from the horizon, the field decays, but our attack is in 2010 find that derivatives of the field blow up with time. In the axisymmetric case, for axisymmetric case, he cannot determine the growth of the derivatives, and together with some collaborators, we found the actual growth of the field on the horizon of an extremal Kerr black hole. So these are derivatives transversal to the horizon of some scalar field and with some time along the horizon, so to speak. And the derivatives grow for n equals 1. The first derivative is already growing for late times. In the gravitational case, they grow even higher. So together with some collaborators, we've determined the growth of the field on the horizon of an extremal Kerr black hole. So this means that extremal Kerr black hole is not a stable black hole, and that it is unlikely that there are extremal black holes in our universe, because you've got a field building up on the horizon.
Where does the energy come from for this build-up of the field?
So it's extracting energy from the black hole.
Ah, I see.
Yeah. So you're destroying the black. Yes, but in this case, the field is building up. If you could numerically do it and plot it at late times, which nobody can do it because you need a huge amount of numerical accuracy, you would see the field just shooting up to infinity.
But such a result highly depends upon the boundary conditions.
No. This is for any in quotes any sensible initial data. That's the power. That's the power of this.
So you have put that there is a node which grows.
Yes. Yes. Yes.
Which is enough to say that basically
Yes.
typical perturbation
Yeah.
will involve this whole
Well, this happens for any L. The growth will be the growth. The power in the growth will depend on L. Here, I've put the highest growing mode, but if you have other multiples, the growth will be smaller, but you will still grow, and some derivative will grow. Okay, so that's a result. That's an important result for the first part of the talk. The second part are binary spirals and gravitational waves emitted. So probably everybody's acquainted with this. This is the LIGO detection that was published last February. So we've got 3 stages in the spiral: the proper in spiral, so to speak, when the black holes are far away. In here, when there is a merger, the 2 black holes have collided and have formed 1 black hole, but it's still far away from being a perturbation of a Kerr black hole. In here you have the ring down, where you have a perturbation of a Kerr black hole. Here you have the corresponding gravitational wave emission at radial infinity. In here, in the ring down, is where you have the quasinormal mode emission. Okay, so what did LIGO do? Well, just after the merger, they looked at the way the wave behaves, and they tried to match it to the quasinormal modes of Kerr that we have calculated, and say, do they agree? Now, the accuracy here, the signal to noise ratio in the LIGO detection was very, very small. They could only use 1 sinusoidal, so the accuracy is very small, but they could see that the way the field decays exponentially, let me put that in quotes because it's just 1 sinusoidal, and the way the frequency agrees very well with the Kerr, the lowers overtone, the least damped quasinormal mode of Kerr for the mass and the angular momentum predicted for the remnant of the LIGO detection. So this is just some plots of the decay time, which is the imaginary part of the quasinormal mode frequency, and the quasinormal frequency, by which they mean the real part of the quasinormal mode frequency. And this black circle here tells you where the prediction is, and the quasinormal mode of Kerr falls into this region. So happy days, but it's still not very accurate to deal with this. Okay, this is a numerical relativity prediction of the modeling. I'm going to skip this. We don't have much time. I think I don't have any time. Just a few minutes. So this is, how do you solve, so far I gave you the exact solutions of Einstein equations in the case of just a black hole in isolation, Kerr. What if you don't have a black hole in isolation? What if you have 2 black holes moving around, a dynamical situation, 2 black holes moving around each other? So numerical relativity is good for mass ratios not too large, up at most to 1 to 100, and when the black holes are not too far away from each other. When the black holes are far away from each other and the motion is small, you use post-Newtonian theory. Perturbation theory, which is what I work on and what I'm talking about in this seminar, is good for large mass ratios and any distance between the 2 black holes. So in fact, LIGO is not going to be able to detect, is not aimed to detect black hole in spirals in the mass ratios, but there is another experiment, the LISA proposed interferometer. It's believed it's going to fly in the early 2030. It's a European Space Agency mission. It's going to be some interferometer up in outer space orbiting near the Earth, and it's expected to see about 10 to 1,000 extreme mass ratio in spirals. So stellar mass compact objects, whether they're neutron stars or stellar just normal stars, orbiting around a supermassive black hole at the center of any galaxy. In that case, you've got an extreme mass ratio in spiral, and Lisa is space interferometer is going to be sitting here, supermassive black hole in spirals. LIGO is sitting here, which is not in the extreme mass ratio. So this is just going back to what I said before. How do you deal with this? Well, you linearize Einstein equations. You have some background metric given by the Kerr metric, some gravitational perturbation of that, and the gravitational perturbation that gives you the gravitational waves. In this case, we're interested at radial infinity, satisfies some wave-like equation, just like the scalar field. Now, what happens? Well, you have the small black hole emitting these small gravitational waves. These gravitational waves, like I showed in the video before, are being scattered. So let me show that video before. Now you can look at the small object here. This is a small black hole orbiting a supermassive black hole. This small black hole is orbiting around. It has emitted that impulse, and that impulse is going around the black hole and coming back to hit this compact object there again. So the field emitted by the black hole at some time in the past is going around the Kerr black hole, the supermassive black hole, and is going back to hit the small object again. So there's interference between the field produced by the small object hitting it again. So it's a self-force.
Do you have any idea what is the mechanism for this sudden emission by the other object?
Well, it's
Would it suddenly emit radiation?
well, it's not suddenly. It's emitting radiation all the time.
Yeah, right.
So you have to calculate radiation emitted all the time. So in fact, this.
But you had this idea that this is an impulse.
Well, I calculate right, but you. Yes, but you have to calculate the impulse emitted at every single time. So you have to.
You're using green function that allows you to calculate the
So in here, the self-force is going to be at a certain instant on the small object is going to be you can calculate it as the integral of the retarding function over the whole password line of this particle. So here you are integrating, you're adding the contribution from each impulse at each time in the past of the particle. So the particle is emitting that impulse, so to speak, at every time in the past, and every time will go around the black hole and come to hit it again. And you have to include the contribution from all those impulses all the way to the past.
But the solution of linear gravity highly depends upon the gauge.
That's right, that's right.
Which simply
That's right.
that you may do everything you wish with it.
No, you usually use T. No, I would disagree. You use TT gauge and then
But if you change gauge,
Okay. Okay, so I agree with that. So
most reasonable gauge can be gauged away. So
Okay, well-
so that's no.
okay, so let me say so it's the gravitational, not in the scalar case. In the gravitational case, the gravitational self-force is a gauge-dependent quantity. So what does that mean? That together with the value of the gravitational self-force, you have to say in which gauge you're dealing with. Okay, that's what it is. I have two results, and the second one is going to concern about gauge invariant quantities. The first result here is the scalar self-force. This is a plot of the scalar self-force. So we use this green function method, which is a totally new method, and it allows you to have a deep understanding of how the self-force comes about. If you go back to the video, it's coming about because of the scattering of the waves, because of the non-satisfaction of the Huygens principle in non-flat space-time, and because of the way the null geodesics are orbiting around the black hole. That gives you a deep understanding of how the self-force comes about and how the small object is deviating from a geodesic of the background space-time of the Kerr black hole. And it's coming about because of all these impulses all the way back to the past are moving around the black hole and are coming back to hit it. So this gives you some deep understanding of the physics lying behind this self-force and the motion of the small object around the Kerr black hole.
This self-force that you're mentioning is something like a radiative reaction in the traditional language of electromagnetic
No,
waves.
because
No?
this
Is
small
it?
object is considered to be a test particle.
Yeah, but there is still a radiation reaction if it
Yes.
It's radiation. Then
Yes.
Yes, a sort of, but of a sort which is not present in the flat space.
Right. So
There, everything radiates away.
Yes.
And never comes back. Right?
exactly. So this is the equivalent. I put equivalent in quotes. This is the gravitational equivalent in Kerr spacetime of the electromagnetic self-force in flat spacetime due to an accelerated electrical charge coming. Now, there's crucial differences to it, so that's why I put equivalent in many ways. Like the director was saying, in flat spacetime, the radiation just is emitted away and doesn't come back to hit you. There's an instantaneous bit, which is the one that comes from that gives you the Larmor formula and so on. And I'm not including that in this equation here. So in the equation here, you would have this other instantaneous term that we don't really care about. It's easy to calculate, and it's there already in flat spacetime. This term here is only there in Kerr spacetime because the waves are not just emitted away, they're trapped in some way, they're curved around, they're scattered around, they come back to hit the small object again. This does not occur in flat spacetime. This is not the origin of the cell force, the electromagnetic cell force in flat spacetime.
It's a kind of non-local effect.
It's definitely, exactly.
What I can imagine
Yeah.
is when I think about the photon, you have this small thing emitting photon, and then the photon goes around the
Yes.
black hole and it's absorbed again.
Exactly.
If you have a flat space-time
Yeah, in that space it's
and
scalar.
with a hole in it, right? So that there will be topologically non-trivial paths which photons could take. Some of them probably wind around this small, not a string or something like that.
I'm not sure about that, but as long as you have photons going back to hit where the particle is, you definitely have that. And you can have simpler spacetimes where this is happening. Okay, so this is a calculation of the cell force coming from this green function integration that gives you some physical insight into what's going on, and it's actually useful for practical purposes as well. Going back to the point that you were making before about gauge invariance, the cell force is not a gauge invariant quantity. In order to compare with other methods, numerical relativity, post-Newtonian methods, we need to calculate gauge invariant quantities. So you can define gauge invariant quantities. It's important for this reason. It's actually, some of them are of interest and relevance for gravitational wave astronomy. One of them is the frequency of the innermost stable circular orbit. So this is the radial potential for time-like geodesics in Schwarzschild spacetime, but it's similar in Kerr. So what this means is you give a certain angular momentum to the geodesic, and where the minimum of that of the potential is, you've got a stable circular orbit. As you decrease the angular momentum of the time-like geodesic, the radius of the circular orbit is getting closer and closer to the black hole, and there is a minimum value for the angular momentum at which you can have stable circular orbits. The radius, that minimum, the circular orbit that has the minimum radius is the so-called innermost stable circular orbit. Now the frequency, the angular frequency of a particle on that ISCO is a gauge invariant quantity, and it is an important quantity for gravitational wave astronomy. So you can easily calculate what is the value of that quantity in Kerr. Okay, for a test geodesic, if you don't take account at all the back reaction, the gravitational field created by the small particle, that's a very easy calculation. But what if you take into account the gravitational field created by that small particle? Now we're doing perturbation theory, so we calculate the effect of that to linear order in the mass ratio. So it's not a test particle anymore, we're letting that particle to have some non-zero mass. It's a very small mass compared to the mass of the Kerr black hole at the middle, at the center. So we calculate the correction to the Kerr value, but it's a correction to linear order in the mass ratio. And this is a plot of this gauge invariant quantity as a function of the angular momentum of the background spacetime. So this is a relevant quantity for gravity. By the way, these results that are not published yet, but it should be published in the next month or so. So these are different values of the angular momentum of the Kerr black hole. So this is a relevant quantity for gravitational wave astronomy, and it's a gauge invariant quantity. Okay, so just to sum up, we've used this spectroscopy method of decomposition of the green function in the complex frequency plane to study the stability of the black holes. In particular, we've found the growth rate on the horizon in extreme Kerr of the field. We use it to calculate the cell force, and we obtain corrections due to linear order in the mass ratio for gravitational wave observables. And that's not meant to be like this. In the future, there's a lot of work to be done. For example, it would be interesting to add some cosmological constant to Kerr to see what are the stability properties of the Kerr black hole. Because the universe is, the experimental data tells us that we are in accelerated expansion, so that's modeled by the CTP universe. LIGO's matching of the observed data with the quasi-normal mode ring down is relatively poor because the signal to noise ratio was quite low in that regime, but the LIGO data is going to be pouring in the next few years, the next decades. Then we're going to see a massive explosion in gravitational wave astronomy. Other interferometers are going to come into place, LISA in the early 30s. But LIGO data, the signal to noise ratio, it's going to be improving, and hopefully the signal to noise ratio in that regime in the ring down is going to be improved. And you want to match that to the quasi-normal mode ring down. They just use the least damped quasi-normal mode. It would be interesting to include other quasi-normal modes. I gave you in that plot many quasi-normal modes. You can include many quasi-normal modes, and the branch code has not been included. We included some corrections, the logarithmic corrections to the branch code. It will be interesting to include everything that we know in perturbation theory in order to match that with experimental data from LIGO. Also, for the LISA detections, we're going to need second order cell force to get accurate, to calculate accurate waveforms. We're far away from calculating the second order cell force. When I say we, there's many groups in the world calculating these involved technical calculations, but the aim obviously is by the time LISA goes to flight, we have second order calculations of the gravitational cell force. And I haven't talked about this, but some other part of my work is investigating quantum properties of black holes, and you can use the green function for that as well. So, dziękuję for your attention. Yeah.
Question about these observables. So when you speak about the observables in the gravitational wave astronomy, this means the shape of the waveform.
Yes, that's right. Yeah.
Do you think of any other types of observables, for instance, when the black holes are not in vacuum, but there is some matter around and this matter is emitting light?
Oof.
What type of observable would you have apart from this?
In the case of matter being or the matter being around. So things get complicated when you've got matter being around, and I haven't dealt with that, although it's astrophysically extremely important because black holes are surrounded by matter. In the case, it is not easy enough already in the case that there's no other matter around. I'm not aware of observables in the case of matter, and I'm not sure it's an easy calculation to do. Yeah.
Speculate.
Actually, the position of
This is observable for us when you have a vision.
is, for example, for me, that I deal with accretion disks, and in the case of massive quasars, large black hole mass, large accretion rate, the mass of the disk is comparable to the black hole.
Right.
So in a sense, I could, for example, use your correction to the ISCO position.
Right.
The problem is that my disk is kind of extended.
Yeah.
It's not a point. in
Yeah, yeah.
sense.
Yeah.
But in principle, well, perhaps using few perturbations or whatever, or summing or 2 or 3 or 5
Yeah.
of your point
Yeah.
masses, I can get the
Yeah.
correction to ISCO, because ISCO for us
Yes,
is
this is observable,
Yeah.
the frequency of something.
Yeah. I mean, there's two issues. One is the one that you just said, that the fact that it's an extended, very much an extended object that you've got there, instead of a almost point-like object that we have here. The second one is the fact that the mass of the accretion disk would be comparable to the mass of the black hole. When we're doing perturbation theory here, which is an expansion in the mass ratio. Now, what has been proved is that you can use perturbation theory to give you good results, not only for MRIs, but also for IMRIs, so intermediate mass ratio spirals. So in fact, it's been shown that the regime of validity of perturbation theory is a lot wider than it was expected. So in the case of 1 to 100, easily perturbation theory is already giving you very good results, accurate results, even though the mass ratio is not that strong. So there is tentative indications there that one could use perturbation theory beyond what one could expect. The issue about the mass not being point-like, I'm not sure how I would get around that. Yeah.
Okay, just one remark. I wonder whether the corrections go just due to the presence of a massive disk not be larger than this thing here. But I don't know. Nice to see.
I don't know, I did not consider. I always use the Kerr black hole, but I do worry because my disks are massive in some cases.
Having said what I said, there's a good thing about your setting, which is there's a symmetry in that setting, I would imagine, that there isn't in my setting. You've got the accretion disk, there's a so one, yeah.
It's more or less in the equatorial plane.
Yes, yes.
Apart.
Yeah, so one could exploit the symmetry that you have in that setting and that we don't really have in that setting, but
I also have one question concerning this extreme mass ratio Inspirals we consider. So there is another phenomenon which I think could be very easily studied with your setup, namely the influence of the small body on this large black hole, tidal heating and things like that. Have you tried to consider that? So
no.
how these perturbations affects this central black hole? It probably does somehow.
Yeah. Yeah, we haven't. We're neglecting the. Yeah, we're neglecting that. So.
Just another phenomenon you could study.
Yeah. Yeah.
And last question, in this extreme mass ratio Inspirals, you don't consider the spin of this smaller body?
No.
It's
Yeah, so that would be a higher order effect. So I think that's been done for the case. I mean, there's different orders going on here. Even for the cell force, there is a conservative cell force contribution and an adiabatic cell force contribution. So the cell force isn't just the energy being radiated away. There's a conservative part that is changing the periastron advance and other conserved quantities. Now, the adiabatic effects are of lower order, are more important than the conservative effects. So I said about calculating the second order cell force, we're only interested in the adiabatic part of the second order cell force. And the spin, I would say that in the first order mass ratio probably comes in only at a higher order. So it would only matter to higher orders. I think that's been calculated for the spherical case. I think people have done this recently. In the Kerr case, nobody has considered that. But at some stage, I mean, certainly in some order they will matter. I'm not sure that will matter for Lisa, but at some order it will matter, yeah.